Hi, good morning, Math 218. Uh, this video today is the first one I'm recording is basically a recap of the last lecture and a half, maybe summarized. It'll go a little faster, and because you did see it already, but this is a recap on conditional expectation, conditional variance, and Rao-Blackwell's theorem, and minimum variance unbiased estimators. So these will be pretty short. This might have to take two videos because I can't go over too many minutes and still upload it in a reasonable amount of time. So we'll just see how far we get it. It might be two. And then from here we'll continue into the next sections on methods of finding estimators. So what we'll just do is write notes and I'll talk. So it'll be like a lecture hopefully, and only I'll write it down. So I wonder, I actually want to review some notation. So let's see. So first thing is, some notes on notation. So just to clarify some of this for you. So if we have something like e, g, x, where x is a random variable, y equals y, well, you can see from the definition of this, for example, if these are continuous random variables, then this would be, so we'll write here continuous. But it's similar if they're not continuous. Then this is the integral gx. It's the definition. And this you can see is a function of little y. So this is a of little y, which is just some possible value, which is a possible value of y. Now if I write e, g, x given y, then really all this is it's just replacing little y with big Y and saying it's a random variable. It's a function of the random variable y. So you don't really usually see it written this way, but I don't see anything wrong with writing this. I have g little x, and here I have fx y little x, and in here I could just put the random variable y, because it's just going to come out of that integral anyway. And you can say this is a function of RVY. Okay, so okay, so just want to be clear about that. So if you want to compute this, you can do it either, if you want to compute this one, you do it this way. If you want to compute this, you do it this way. Okay, so we have two properties on conditional expectation, one property on conditional expectation, one on conditional variance. So we're going to have property one. I know I'm going fast, but we did have this already, so hopefully, and it's in the book too, so hopefully it's review more than anything. So E g of x is equal to E, need another one here, the expected value E g x given y. Okay, expected value of g of x is equal to the expected value of g of x given y for any RV y. This is easy enough to show. We can show this by because, so proof. Let's do the continuous case. Sorry, you can't really read that, right? Yeah. Okay, so for the continuous case, we'll prove it. We'll just say E of G, big X given big Y is equal to, well, I'll just substitute in the definition here, right? So this is equal to E so it's up there, right? G little x f x given y little x given, can use big Y if you want, dx. And right, yeah, I'm having a little trouble writing the, next to this thing I'm propping the camera on, but I'll be okay. We'll figure it out for better for next one. So this is, now I have a function of y. I want the expected value of that function of y, so we know what to do there. We have another integral with respect to y now, and this is the function of y, so I put this in, r gx f x given y x given little y now, because I'm taking this, taking the expectation of this function of y, dx. Now I need the marginal distribution of y, dy and dy. Now, here's where you need to use continuity properties and actual analysis to argue that you can bring things inside integrals and combine the integrals, but you can when in really every situation in statistics. So I'll bring this in here. I'm going to bring fy of y in here and make the joint PDF. We know the definition of the conditional is the joint divided by the marginal. So multiplying through by the marginal, I get the joint back. And I get just this again, r gx f x y dx dy. If you want to see it even further, you know that this, you can integrate with respect to y now, and you get integral r g of x f x x dx e of x. Okay. Okay, I gotta figure this out better. Okay, right. Okay, so let's see maybe how we use this property with one example. Did a couple examples last time. So example, suppose y is exponential and the mean equals theta, and now let's let theta be, say, uniform, 0 to 5. Then e of y is just e of y given theta, which is equal to, well, I do the inside one first. What's e of y given theta? Well, the mean is theta, so this is just e of theta, which is equal to 5/2, right? Let's do another one. Another example. So if I do another example, maybe I should do this just to keep myself I'm almost have to stop already, but we'll do one more example. Suppose we have, let's say, x or y is uniform, let's say 0x, and x is uniform, let's say 1, 5. Then e of y is e of y given x, which is equal to e, what's e of y given x? X over 2. So we have 1/2 e of x, which is 1/2, and e of x is 3, so we have 3/2. Okay, I have to stop this one.